Okay, so my name is Brent Justice, and I'm currently a senior at Purdue University, and I'll be graduating this May. So currently I do a lot of work out at this place called the Purdue Zucro Propulsion Laboratory. Essentially, it's a student-run rocket lab, and there are all sorts of tests going on out there from small rocket engines to gas turbine engines. And recently I've been taking on kind of the role as data acquisition and control lead. So essentially, we've got a whole bunch of different teams of students working on projects, but not a lot of them have experience or skill with National Instruments hardware or LabVIEW. So I kind of take on that role. And the way that I've done that is I've actually created an application that serves as kind of a single platform for running all of these different experiments. So one thing that we do that's unique is that our DAQ software is completely config file driven. And what that means is that we don't actually hard code any of the channels or hardware into our software, into LabVIEW. We actually have config files written in Microsoft Excel that map all of the hardware to the mnemonics that we associate with channels. This allows me to task the different student groups with creating these config files, which are generally easy to do, such that they don't have to worry about LabVIEW or doing any sort of software programming. So let's take a look at what that looks like. So we can see here, these are 4 different config file folders. I'm only showing the template folders here for simplicity, but we run a different we run a lot of different hardware out at Zucro Propulsion Labs. We run some PXI chassis, one of which has a bunch of 6368 DAQ cards in it. We also run a string of PCI 6115 cards, and we've got a couple of students running USB 6343 modules. So I think the best way to illustrate the power of this software is to actually take a look at an example. So we're going to look at an example of an experiment that I actually conducted in the fall. And this was for a pre-detonation tube experiment. So it's a very simple experiment. Here is the P&ID diagram that I put together for this experiment. But essentially we have a small tube here, and we flood that tube with gaseous oxygen and hydrogen, and then we ignite that mixture with a spark plug. And we get a real nice CJ detonation wave coming out of that tube. So you can see that we've got our K bottles in the far left here. We regulate those K bottles, pipe it through some check valves. We've got some pressure transducers to see what the head pressure is. And then we've got some fast-acting solenoid valves for controlling the flow into our detonation chamber. So a very simple experiment. And let's take a look at what that looks like in the form of our config files. So here's our pre-det experiment. Here are the config files for our pre-det experiment. And here's our data wiring list. We'll take a look at this here. And you can see that we only have 2 pressure transducers that we're concerned about for this test. And those pressure transducers are mapped to these physical hardware channels. In this case, we're using a PCI 6115 card. And you can see that we set this up to be suited differential with these slopes and offsets, and all of this other glorious config file information. Okay, so next we'll take a look at our control wiring list. Again, you can see that we've got 5 different items that we're going to be controlling here, and these are going to be controlled with digital output channels. In this case, we're using lines 1 through 5. And we've got a couple of solenoid valves. These solenoid valves are normally closed. However, we could operate normally open solenoid valves if we wanted to. We also have a safe state. In the event of an emergency, we would be able to command everything into a safe state in order to put it into a good configuration. Alright, so this is the most important part. This is our auto sequence. So if we wanted to, we could software time all of our digital output ports to about a millisecond of timing authority. That's about as good as you can get with software timing, meaning running off of your software clock. However, that's not good enough for us, especially when we're running rocket tests. We want to get very, very good timing authority on our digital output ports going to our valves and whatnot. So we actually hardware clock all of our digital output lines. And what that essentially means is that we buffer waveforms to the hardware, and those waveforms execute with the help of a digital output sample clock. So you can see here that we actually assign a counter channel to be that digital output clock source. And the software will handle the initialization and the running of that counter channel for that purpose. So let's take a look at our auto sequence here. You can see that at time equals 0, we go ahead and open our solenoid valves and we start the flow of our gaseous hydrogen and oxygen. And at about 20 milliseconds, we stop that flow. At about 14 milliseconds in, we start charging our smart coil, which is going to create the spark. And at about 23 milliseconds in, we discharge the smart coil, and that essentially gives us our ignition. At this point, the solenoid valves have closed. And lastly, we have a simple initialization file. This simply lists all of the different config files that we want to load into our software. This essentially allows us to get our tests running fairly quickly. Okay, so I think we're ready to go ahead and run our software now. So this is our top-level GUI. From this launchpad, we can launch our different schematic GUIs, as well as various utilities and plotting tools. So the schematic GUIs are very simple to make. I can have students make these, and then I will wire up the back end, which tends to be super simple. A lot of the difficult software tasking is actually abstracted into DAQ control and other utilities within the software. Regardless, this is our pre-DAQ GUI. You can see this closely matches our P&ID. This experiment is very simple, but again, you can see the two pressure transducers we're interested in are fast-acting solenoid valves, and then a downstream liquid injector valve that allows us to inject water downstream of the detonation and see what that looks like. We'll quickly take a look at some of the other experiments going on. So this is a small rocket engine that another group of students is currently using this software for. Here's a combustion tube experiment that another group of students is running. And here is an igniter experiment that another group of students is running. Okay, so I think we're ready to go ahead and load our config files now. So we'll boot up DAQ control, and we'll go to load config file, and we'll select our initialization file that we discussed earlier. And we can see that our software starts to boot up nicely. We can see that we have loaded a data collection file as well as an auto sequence file. And we'll run through our tables here just to take a look and double check. But here we can see our digital output wiring, and that looks good. Here is our analog input wiring, and that looks good. We can decide whether or not we want to log these here. And lastly, we can take a look at our auto sequence. So this is kind of a visual cue that allows the operator to look at the auto sequence and see whether or not their Excel timeline is indeed doing what they want it to do. So we can see that our data logging stays active for about a second. So we get about a second of data logging. And if we zoom in here on our actual valving events, we see that our solenoid valves stay open for about 20 milliseconds. And our spark plug discharges is at about 23 milliseconds. So about 3 milliseconds after the valves close, the detonation occurs. And that's what we want to see. So that looks good. I think we're ready to get our test started now. So the first thing that we're going to do is we have the option of manually acquiring and recording data without running an auto sequence. So we're going to go ahead and just start data reading. And you can see that now that we've started reading data, our pressure transducers have populated over here, so we can see what our live data looks like. If we wanted to, we could record that data, and we could stop recording. All right, I think that looks good, so we'll go ahead and stop acquiring data. And I think we'll go ahead and arm our auto sequence. So when we arm our auto sequence, we're actually preparing the software to run the auto sequence, which means that we are creating and exporting our digital output waveforms to the hardware and preparing those to start. We are also configuring the data collection in a way such that as soon as the auto sequence starts, the data will start collecting and start data logging in sync with the auto sequence. We also see that our two solenoid valves, which we had manual authority over earlier, are no longer able to be commanded from the GUI. And that is because they're currently configured by the auto sequence. Now, the liquid injector valve, it is not appearing in our auto sequence. As a result of that, we are still able to control that manually if we wanted to. So I could actually do that even though we are armed for an auto sequence. Some operators don't like that though. When they have an auto sequence armed, they want the GUI completely locked. So we have the option to do that here. Okay, so I think we're ready to run the auto. we've checked everything. Everything looks good. So we'll go ahead and run this. Okay, and that was it. So you can see we're no longer collecting data because we stopped data collection after a second. And our GUI is still locked, so we're going to unlock the GUI. And now we have control over our valves again. We can actuate these manually until we decide that we want to run another auto sequence. Okay, so another strength of this program is that we actually buffer all of our live data to a circular buffer for approximately 10 minutes for each channel. That allows us to actually pull up live plots. So we can open up a single plot utility here, and we can see that we currently have 2 channels in memory, and that's our 2 pressure transducers. So we can plot those. And as of right now, we're simply using a simulated PCI card, so it's just a sine wave, which isn't too interesting, but still gives us an idea of what this utility is. Another thing that we can do is, like I said, data is buffered for 10 minutes. However, users have the option of only viewing 5 seconds or so, or how much ever time they want. So right now, we'll just view 5 seconds of live data. You can see that the trailing edge is cut off. There's also a multiplot tool, and that allows users with a lot of different channels to view all of those channels simultaneously. So we'll configure this plot to display pressure transducer 100, and this one will display pressure transducer 200. And that's pretty much it. This has been in development since early January, and it's already being put to good use here out at Zucro Propulsion Laboratories. If you have any questions, please let me know. Thank you very much for your time. I look forward to hearing from you.